All right, I keep forgetting to track the name. Let's see.
All right, I am getting your first assignment to you today. I guarantee it. I've mocked out exactly what we're doing, and it's going to be a bit of a behemoth. So I apologize in advance, but I say that so that people get started early rather than waiting and getting overwhelmed and getting started late. So I will get it to you today. It'll be due a week from tomorrow. It's, as far as I've mocked so far, I may change this or decide to change this before I post it, but I think it's about 22 book problems, which there's quite a bit there. We've also gone over a bit, and we will be going over a bit. So not all of it we have covered exactly at this point, but you can probably do the first half to 2/3 of it as of now slash by the time we're done with today slash tomorrow. So the last little bits of it will be coming in over the next couple of days, but you should have plenty of time for those last few problems by the time we cover the material. Should be within the next couple of days. I will have significant office hours to help. I know that this will be a little bit different probably than assignments that you've seen in prior classes before. I plan to alternate between some theoretical book problems and implementation problems or projects. By the end of this quarter, you should have at least 2 or 3 reasonably sized programming projects to put in your code portfolio. I will try to make sure that we're not just focusing on one thing, and that being book problems or straight book problems like a math class. But the material that we're covering right now plays very well into getting practice in that way. So it makes sense to start there for our first assignment. But as soon as we're done with this assignment, we will be doing code and implementation for the next couple of projects. But that is what's coming. Question?
So is this assignment just like function analysis then?
A lot of it will be complexity analysis, and then we will talk about 3 different ways of analyzing recurrence relationships. So there will be some problems on the 3 different ways to analyze recursive problems. Yeah, a lot of it's just a little bit of code analysis, but also just what theoretically can you do with big O notation, big omega notation. And so I will be assigning, but not assigning. I'll tell you what I mean. The chapters from the book that are covering this material, my plan for this class, I think I may have mentioned this on the first day, but it's worth a refresher anyway. The book is a little on the denser side. I don't like it as an introductory text. I like it once you understand something intuitively, then it cements it very mathematically and logically. So I plan to introduce things at an intuitive level in class and then assign the book and the problems from the book as a, now that hopefully you understand this intuitively, come see me in office hours if I can help with that. Then that will become the practice of material that we've covered and really applying it to slightly more complicated problems that we've seen in class. And again, I'm here to help you through any or all of that. I anticipate those office hours being full. That's just the nature of offering office hours and doing my best to make them useful. I will be inviting as many people into my office as I possibly can fit in there without violating fire codes, to make sure that you're not waiting outside of my office for a long period of time before you get help. I don't want to waste your time. So that will be coming later today. I will give you the associated book chapters that go over the material of those, so that becomes an additional reference. I will also be posting pictures of the problems to Canvas, so that if you don't have the book, you don't need the book in order to see the problems. We just be missing out on some of the supplementary material that goes over the material that we've covered in class. There's nothing in the book that hasn't been covered in class. They're just additional kinds of examples, etc. So you don't need the book as a supplement to the course. I just think that it's incredibly useful for the review of the material before we dive into it. So, yeah, any questions on that?
I don't really have the textbook talking about like.
It's on GitHub.
Oh,
So what?
it is not.
We will figure that out. We'll make sure you have access to
It
it.
says here, you currently have no materials associated with this course. Is that on GitHub?
Yeah, so if you look it up, you can find the PDF on GitHub.
Introduction to algorithms.
So of course, just type in the name of the book in your.
I don't hear any of this.
Type in the name of the book and then put in GitHub, and then you'll find the PDF on GitHub.
Okay.
Excellent. Short-term memory loss aside.
Sorry.
No. I'm just saying that I can't officially hear you say that. That said, that's a great resource for people who might want access to it without the middleman of paying for it.
It's
But I
also
didn't say
free
it.
in the library,
It's also free in the library.
so you can just.
Perfect.
That's a temporary.
So yeah, there are resources out there if the money to get a physical copy or a digital copy of the book does not make sense for you right now, there are ways around that. Not something that I can easily help you with morally, but there are ways. Yeah.
I would never advocate. Yeah, file type PDF or working with the be a great shame if they actually looked at actually probably have.
Absolutely not. And his archive is what?
Oh, yeah.
All right, the other big announcement is we've had a bit of a change in our TA/grader. I don't know what I want to say, but one of our graders, the one who introduced himself at the beginning of the term, has had a bit of a family emergency and may not be around physically for the remainder of the term, and it's up in the air as to whether he will be available to grade at all. So I've met with the other grader. I've made sure that that's very clear to the other grader. A bit is up in the air with regards to that. But as I get more information, I will pass it along to people. This may affect things in a class this large with regards to turnaround times, since there's only going to be one in-person grader. So things that require things that are in person. So it's changed the TA's office hours. That's going to be Monday and Wednesday from 11 to 1 now instead of 10 to 12, perfectly overlapping with me. I'm working on getting him a cube, but if not, then he would be available in the student lounge, which is right over there, 305 at that time. So I'll pass along more information for that as I know it, but it sucks for everyone. And I will certainly be keeping that in mind. If there are delays in grading, I will make sure that I keep that in mind with regards to when exams happen, what is on said exams, any curving that I do at the end of the quarter. If I am not okay with how long it has taken to turn something around, obviously I can't hold that against you. That's an important resource for you ahead of studying for an exam, etc. So I can't hold that against you. And we will continue to be in conversation as it affects you about what I can do to meet you in the middle of the pain that causes. It's just something that's outside of everyone's control. All right, that took 10 minutes of class. Sorry about that, but lots of announcements. Any questions before we dive into recurrence relations and how to analyze recursion problems? Okay, off we go. All right, we had kind of introduced this idea, but not gone into detail very much. We talked about this concept of using T of n to analyze the complexity of a recursive problem of size n. And what we're going to be doing is we're going to be breaking this recursive problem of size n into its number of subproblems. So merge sort, you took a problem of size n and you broke it into two problems of size n over 2. If you're doing something like reversing a list, you're taking a problem of size n, and when you call that recursively, you have something that is problem size n minus 1, because you're going to strip off the first element of the list, and when you return from the recursion, you're going to append it to the end. But when you call it recursively, you're calling it with a list of size n minus 1. So we care about how many subproblems are there and what are the size of those subproblems. So when we talk about T of n or T of something, that's what we were talking about. The n is the size of the problem, and we'll relate that expression based on T of n over 2. That tells you that there is a problem of size half of n. 2 times T of n over 2 would say there are 2 problems of size n over 2. And that's exactly what merge sort is doing. It's breaking a sort this array of size 64 into 2 sort this array of size 32. So we'll see how that appears in the functions as we go. The base case will just be T of some constant, the size of the base case problem. So usually we have T of 0 or T of 1, because when we hit that base case, the size of the list is 1. How easy is it to sort a list of size 1? It's trivial. It's already sorted. That is the base case. So we need to relate 2 things when we relate a recurrence, a T of n that is the recursive case. How do we break down the recursive case into its components? And a T of the base case size. Some constant, 0, 1, occasionally 2. So T of a constant, T of n, and we relate that in terms of the complexity of the problem. How many subproblems are there? How large are those subproblems? And then we will add on a term that is the cost of the combining step. Once we return from the recursion, how much effort, what is the complexity of combining the solution to the larger problem given the solution to the subproblems? So we will very frequently see T of n minus some constant if we are turning a problem of size n into a problem of size n minus that constant, or T of n over some constant, saying that that constant is breaking the problem into subproblems that are a portion of the size of the original. So yeah, multiple copies of the T term if there are multiple subproblems. In merge sort, there are 2 subproblems, so we would see a term that looks like T of 2 times T of n over 2, plus however long it takes us to combine a solution from 2 sorted subarrays into 1 sorted array. That process would be a theta of n, or some concept like that. If it's merge sort, then it is theta of n. It's going to take us time proportional to the size of the array to recombine the solution of the sorted array given the 2 sorted subcomponents. So the additional term is the complexity of combining the subproblem solutions. So that is basically recursive. We're taking the complex problem, we're breaking it down into multiple simpler solutions with the idea of eventually reaching a base case. So how complicated are the subproblems? How complicated is it to put together the solution? We're there. If we don't know the exact formula for something, we can use inequalities, giving us upper or lower bounds with regards to how complicated the solution or the breakdown is. Usually we won't need to do this. I won't give you very many examples of this because I'll let you read about it in the book. I don't usually assign too much with regards to this, especially early. But if that's the case, we can state the solution in terms of O notation or omega notation because we end up with upper or lower case bounds on the recurrence. So if we make any assumption that the recurrence for this, here is an upper bound for this, then when we come up with a function for its complexity, that's also an upper bound. That's a worst case. We should use big O notation. Okay, a lot of introduction, a lot of words, needs an example. Let's go to it. So let's look at if we wanted to do a linear search recursively. How would you implement a linear search? So in a linear search, we have a list. We'll call it an array for the sake of thinking about it. And we want to write a recursive function for that linear search. So let's think about first, what is the base case? Yeah.
If what we're searching for is in the first position.
I would argue we're probably doing that every single time. We're going to look at, is it in the first position? And if it's not, then we're going to strip that first position from the array, pass into the recursive call that same array with the first element removed. But we're going to continue to do that until what terminates this procedure? how do we know we've reached a base case where we can determine either it's here or it's not in the list? When the size is 0, yeah. Yeah, so if we pass in a list of size 0, we know it's not in the list. Great. The recursive case, just described it, but we're taking in a list of size n. We're going to look, is it in the first position? If it is, great, we return it. If not, then we're going to recursively call this on the array with bounds now 1 less. We're going to, wherever this starts, we're going to start at 1 further and pass. So let's look at what the recurrence relation looks like that might describe this. So we're going to describe this in terms of the complexity of a list of size n is made up of 2 components. It's the complexity of the list of size n minus 1, because that's what we're going to recursively call, plus some constant. And that constant is going to be how long it takes for us to look at the first element, determine whether the first element is what we are searching for, and then call the recursive function. So cost of searching n elements, broken down the cost of looking at a single element, plus the cost of searching n minus 1 elements. We don't know what the cost of searching n minus 1 elements is, but we can use logic to figure out how complicated it is to look at the first element, because that's independent of the size of the list, to look at the first element of the list and determine, is this what we are searching for? So to do this, this is just an array get, right? We're going to look at a position for an array get. So what does that cost? Asymptotic. A single array get at the first position. Constant time. So this C can now be replaced and considered to be something that is in theta of 1. There's no reason that this should ever take longer than that for any input size or order, or there's nothing about the underlying data that would ever cause this to be in an order that's not constant. So we can use theta notation and relate it as constant, which is how we're going to read theta of 1. So now you could rewrite this plus c as just now t of n equals t of n minus 1 plus theta of 1. It doesn't tell us exactly how long that's going to take, exactly how many constant operations it is, but it tells us that it is constant and does not scale with the size of the input. So this is not everything with regards to a recurrence. This is just how you would construct such a recurrence. We now need to analyze this to figure out what is the cost of the linear search. We can use our intuition to come up with an answer. If you were to implement this in code, how long would it take for you to linearly search an array of size n? What asymptotic order would that be in? N, the size of the list? Yeah. So we need some way of converting this recurrence relation notation down into the actual order of the function. So we want to conclude that this is going to take theta of n time. So we're going to, we can see how by the nature of the recursion, thinking about the code, we end up with a base case and a recursive case. From the base case and the recursive case, we can write recurrence relation notation. But now we need to figure out, okay, how do we go from the recurrence relation notation to this asymptotic order for this recurrence? How long will it take to do this linear search? So to do that, we're going to implement, we're going to call the substitution method. And we're going to, what I'm going to call, unfurl the recurrence over multiple calls. We're going to try to look for a pattern for the mathematical progression of how this term expands over time as we make more and more recursive calls. So we will start with our base t of n equals t of n minus 1 plus c. We could replace this c with theta of 1. In fact, I would probably prefer to replace this at this point with theta of 1. But we're going to try to, at this point now, replace t of n minus 1 with t of n minus 2 in this function. So how do we define t of n minus 1 in terms of t of n minus 2? What would a function for t of n minus 1 look like? T of n minus 1 equals, where the only variable in that is t of n minus 2.
Yeah.
What would that look like?
I think I might have a decent understanding. Drawing, but I'm not sure if I'm right.
Let's find out. So we have a guide right here. This tells us that t of n is t of n minus 1 plus c, but if we substitute, that is the worst arrow I've ever drawn in my life.
Trust me, I think I might have drawn worse.
So we can define t of n minus 1 in terms of t of n minus 2 with a substitution of this idea. So if we now have the ability to define t of n minus 1 in terms of t of n minus 2, can we back substitute now and have some function in terms of t of n? Yeah?
T of n minus 1 minus 1.
So we would have now t of n equals, we only want to define this in terms of t of n minus 2. So we had our old, I'll just write what's here and then show what we can do about that. T of n minus 1 plus theta of 1. But now we replace this t of n minus 1 with t of n minus 2 plus theta of 1. And that is now the entirety of the t of n minus 1. And now we bring down the theta of 1 from here. And we again still have t of n now represented solely in terms of t of n minus 2. Continue this process. Can we relate t of n minus 2 in terms of t of n minus 3? Yes, it's the same formula. So how could we relate just this t of n minus 2 term? At this point, I'll get rid of these outermost parentheses because we don't need them. But we're going to relate the t of n minus 2 term in terms of t of n minus 3 plus theta of 1. And then we're going to bring down this theta of 1 and this theta of 1. And we start to see a pattern emerge. Imagine how many times we would need to do this to get down to the base case. How many times are we going through and substituting t of n for t of n minus 1, for t of n minus 2, for t of n minus 3? N times? Yeah. And each time we're adding one more theta of 1 term. So if we're doing this n times, we end up with n times theta of 1. If we have n instances of something that is theta times 1 or theta of 1, then the complexity of this entire problem is theta of n. And that's how we get there. Every single recursive call to this is adding theta of 1, and we need to make n recursive calls in the worst case to find what we are searching for in a linear search. This maps to intuitively, when we think of linear search, it's going to take some amount of time proportional to the size of the list. In the best case, it's the very first position and we're done, but in the worst case, we have to look all the way to the very end, find it at the very end, or fail to find it. Any questions on this substituting or what that means or the conclusion that I've drawn from it? Five seconds to think about. Raise your hand and then think of the question if you know you have a question, but you haven't perfectly worded it yet. All right. All right. So This is everything that we've already talked about. We end up with multiple copies of this plus C. We can combine like terms as we do this. This helps us. Eventually, we repeat the process, substituting T of n minus 2 in terms of T of n minus 3. And we start to see a pattern. So the purpose of all of this is to be able to write a general expression. So given that we have k loops of this process, what does that look like? And the end conclusion to this is that we see that we can refer to T of n as T of n minus k times c plus k times c, sorry. And we see from there that as we get to T of n minus n, we'll end up with T of 0, which is our base case. And then we see that we have k times this theta of 1. How many did we have? We had n of them. N times theta of 1 is theta of n. So this was the recursive case. I'm going to get into what I just mentioned. So when the list to search is empty, we just return failure. We didn't find it. But so we do this recursive case until we reach the base case. In the worst case, that's n times. So when n equals k, then we substitute n wherever we see k. So we get T of n minus n plus n times c, or n times theta of 1. And this gives us T of 0 plus n times theta of 1. And so once we have that base case, we know that the cost of just returning is also theta of 1. So we substitute as theta of 1 plus n times theta of 1, which gives us that term that we can now simplify into theta of n. So we can now conclude that this recursive process has linear complexity. And this matches our intuition of, again, how we would implement a linear search. It makes sense that it should be linear. How do we feel? Any questions about anything that we just covered? We will go into another example immediately, but just want to clarify that before I set you loose on an attempt at this before we come together and solve it. Good so far? All right. Example 2. Binary search. Let's start with, what is binary search? Someone describe this algorithm to me. Yeah.
It takes a sorted array.
Yep.
Sorted.
Sorted list of some kind.
And then it puts in the middle and it's like depending on the, but it cuts it in half and it's
Yeah, it's either given the middle value, it's the query value is either less than the middle value, since it's sorted, that means it's in the first half of the list, or it's greater than the query value, which means it's in the second half of the list. So each iteration, we are cutting the list in half. The place in the list where the query might be. If there are, again, 64 elements in our list, we'll look at the 32nd element, and it'll either be in the first 32 or the second 32. By the time we've done that query, we loop back around, or recurse back around, I guess. We recurse into the problem of the list of size 32. The other half of the list can't possibly contain the query, so we throw it away. What should the complexity of binary search be, given that? N over 2, good guess. It's logarithmic, yeah. So if every time we are cutting something in half, then the number of times that it's going to take for us to search and find is going to be proportional to the log of the size of that list. So 2 to what power is 64? 6, yeah. So if we're looking at a list of size 64, on the first pass, we'll cut the list to 32 elements. In the second pass, we'll cut it to 16. The next pass to 8, to 4, to 2, to 1. That's 6 searches. So it's the inverse of that exponent. 2 to the 6 is 64. If you have a list of size 64 and it takes you 6 passes at most to find the solution, then it's the inverse of exponential. It is logarithmic in complexity. So let's write a recurrence relation for this. Think about how you would implement binary search recursively, come up with a t of some constant for a base case. What is the base case for a binary search? When the list is size 1, so you should have how complex is it for t of 1? And how complex is it for a list of size n? T of n equals how many subproblems do we have? And what is the complexity of combining that solution? Give that a shot. We'll come back together in a minute or two. Feel free to work with people near you. Introduce yourself. You don't already know them.
Okay, so cool.
Good idea. Binary search. Nice. Could be cut inks out. Yeah, I thought I was looking to it.
What did we come up with for the recursive case? So a problem of size n, how do we relate this in terms of however large the subproblem or subproblems happen to be?
Well, you mentioned earlier, it's like, basically cutting it in half, exponentially, so. So we basically be doing it t to, trying to think of the words here, for. So we're doing it n times, but it's divided by 2 divided by some exponent. Number of subproblems, cost of.
So what's the size?
Number of subproblems would be p, wouldn't it? Or, well. Might be wrong, but.
Almost all recurrence relations have these three components to them. We have the number of subproblems, the size of each subproblem, and the cost of combining subproblems. So for binary search, how many subproblems do we have? Yeah,
Well. The.
interesting. Close.
It's not the wrong idea at all.
So number of subproblems, when we have the array of size 64, when we're looking at the next pass on this, how many arrays are we looking through? When we're looking at arrays of size 32.
Oh, 5. Yeah, alright.
There would be 2, but the solution is only in one of them. We threw the other one away. We don't need to look at the other half for any reason. So there would be 2 subproblems if we did something like merge sort, where we needed to sort both halves. But if we're searching using binary search, the answer will only be in one of them. So there's actually only one subproblem here. So the number of subproblems get multiplied by the size of each subproblem. When we go from an array of size 64 to an array of size 32, how big is the successive array? Half the size. So there should be T of n over 2. And then what is the cost of combining a subproblem? In this case, the work that we need to do in order to go from one recursive procedure to the next, if the answer is at the very end, or if the answer is being returned to us, to combine those solutions into the solution to the larger problem. In this case, the combining subproblems is only locating the midpoint. That's the only part. If this is an array or an array list, the cost of finding the midpoint is constant. If this is a linked list, then we'd have to go halfway into the linked list and break it there. So maybe that is linear. We're going to assume that we're using some kind of array or array list. So we add the cost of that. And we're just going to use C or theta of 1. Either one of those is fine here. So this is what gets us the non-base case, the recurrence case, the recurring case for a problem size n. Questions on how I derived that, or what these general 3 components are or mean in a recursive problem? I think that's exactly what I have here. Check my work.
Yeah.
That's right. Didn't quite start over enough. So runtime checking the midpoint is constant. So our C is, we can call it big O of 1. There is no order that is less than that. So I like to call it theta of 1 when we have that type bound. So we end up with T of n equals T of n over 2 plus C. There is a hidden 1 times in front of that T of n over 2 because there is one subproblem. Right? 1 times anything is itself. But in general, I want to note that there is a number of subproblems term to any of these. So let's give you another minute or so. Work together and see if you can figure out the back substitution. If we are cutting a problem in half each time, think about defining t of n over 2 in terms of t of n over 4 and t of n over 4 in terms of t of n over 8, and combining those to get some kind of function that represents the order of the complexity of a binary search call, recursively defined. And work on that for a bit, and we'll come together and have a look at it.
Like. All these. Well. Yeah, but. Thing, I understand that too. I think I understand. That. So interesting. First iteration. Let's be honest.
What have we discovered? Were we able to manipulate this in a way that seems logarithmic? Let's go over what this would look like. So we could use the exact same formula, substituting t of n over 2 for t of n and t of n over 4 for t of n over 2. Then back substitute so that we are taking the right-hand side and substituting it here for the t of n over 2. And we see that in terms of t of n, we have t of n over 4 plus c plus c. So we end up with t of n over 4 plus 2c. We can continue this process. Now come up with the function for t of n over 4 in terms of t of n over 8. That's just t of n over 8 plus c. Again, back substitute so that we are, again, in terms of t of n. And we have t of n equals t of n over 8 plus c plus c plus c. So t of n over 8 plus 3c. In general, we could determine this in terms of a k, t of n over 2 to the k plus k times c. Does it make sense how we got there?
Yeah. Too much sense, I'll say.
That is not a term I've ever heard in terms of sense. Something makes too much sense. So we can now relate, in general, this problem can be solved for a problem of size k. So now we just have to substitute in n for k, and we can see that that is the case. We do need to figure out the base case. So base case when the array size is 1, we solve for t of 1, n over 2 to the k equals 1, n equals 2 to the k. K is log n. Log base 2 again, I should say. Whenever you see LG, it's log base 2. So we can back substitute, getting rid of k, and we see that t of n equals the base case t of 1 plus c times log n. So that's just back substituting, again, substituting k for n and solving for a problem of size n gets us that this process takes logarithmic time. And it comes from the inverse of that 2 to the k. We're looking at n over 2 to the k. The inverse of that is going to be that logarithm, which is how we get there. The other way to think of this intuitively, if I go back to this, is that how many times are we going to be recursively calling this in order to get down to a problem of size 1? This is if we substitute now n to be 64 or some other power of 2, we see that the number of calls, the number of plus c's that we are adding to this is going to be based on the logarithm of the number that we plug in. So if we plug in n equals 64, then we get t of 32 plus 1c. Substitute, we get t of 16 plus 2c. 8 plus 3c, 4 plus 4c, 4 plus 5c, 2 plus 6c, and we end up with a number of c terms that is logarithmic with proportion to the number that we started with. So that is the intuitive way to see why this is a logarithmic time function, a logarithmic time recurrence when we have done this. But the way you're going to want to show it is to go through this work, derive the general term, and then substitute in n for that general term and derive the actual t of n. That's what should be related at the end. But I think that having an intuitive process for getting started, thinking about what is this function? How long would this function take to run? It is logarithmic. That tells you an intuitive answer that you should arrive at. And that helps you to be able to check your work. Make sure that what you have agrees with your intuition. And then when you write out the recurrence, the answer that you get should also map to some intuition about how the problem evolves. So you can plug in a value of something that makes sense. In this case, a power of 2 makes sense. And make sure that the order that you're reporting by the time you're done with this is the same order that your intuition tells you from plugging in that value. So just make sure that every intuition lines up, and that will help. Yeah.
You will also exactly what you're substituting with that.
Yeah. So if we're setting n over 2 to the k equals 1, so that's just going back to this base general n over 2 to the k plus k times c. So we're substituting at that point, we get n over 2 to the k. How many k does it have to be in order to hit n? So 2 to what power is n? It's logarithmic. So what does k need to be in order to hit n? That's inherent here for the base case. We see n over 2 to the k equals 1. And so we can now just solve for n. Multiply both sides by 2 to the k.
Yeah.
Solve for k, it's log n. And that's how many k represents the number of instances of the recurrence that needs to happen in order to solve the problem of size n. So if we solve for k, that tells us the number of times. It's logarithmic with proportion to the size of the input. Great question, great clarification. Does that make sense to everyone else? Can I explain that in some other different way to help that make sense to people? How we derive that? Right, I think that's everything we're gonna end up with time for. I just want to make sure that I've completely gone through this. So that we get to the conclusion that this runs in log n time. All right, we'll come back tomorrow and talk about the recursion tree method. And as time permits, we'll get into the master method. 3 different ways to solve recurrences. But this will at least let you get started on the homework. And again, that is coming as soon as I have time. I also have office hours starting now. I may end up with a meeting. I'll have to check my email and see if I can play that ever so slightly. These slides are added to Canvas as you finish a slide deck. If you like them in advance, I can use the repository where they're housed on something. The reason that I don't share those on Canvas ahead of time is just that we have questions like today, we have these examples, the answer is later on in the slide. So if people are looking at the slide as you go, you're the problem and the solution, we don't quite get the iteration, but I also understand that different people learn different ways. So having the slides in advance where you can be.
Okay, yeah.
Yeah.
Yeah, these are like done differently.
Yeah, that's why if I'm just saying, okay, might as well read them. So what I do beforehand is I read the book, I interpret the book. All of this comes from either the book or additional examples I can pull or in ways that describe what the book does, but in an easier to grasp way, in my opinion. That's why I send people back to the book after class, after we've gone over the material. Now, hopefully you understand it intuitively. Now you can read it more theoretically, precisely, mathematically, and have a better understanding of the book. Not easy to learn from something that is quite that. Yeah.
Okay, so you can post these like lecture 1 file.
Yeah, the lecture 1 slides are up, but I will certainly, if you like the repository, you can choose when to go through what. So feel free to send me an email or repository.
Thanks.
Yeah.